We are recording. Let's go from current slide. And, well, okay, there, current slide came up. We go through these announcements again, okay? You've heard this one before, but maybe not all of you are here. I want to make sure you've heard it, and anyone listening has heard it as well. Today is the last day for first mini-term, okay? Which means about midnight tonight will be midterm, okay? Because tomorrow starts the second mini-term. So midterm should be right around midnight tonight. Now, periodically, oh, and by the way, if you were in a first mini-term course, please do your student course evaluations because those, they opened just last week, and so then they wanted us to make sure every student got it done in a hurry. They sent me a report minutes after they opened and said, none of my students had responded yet. You know, what's the problem? Okay, so anyway, please respond and do your mini-term 1 student course evaluation. Certainly the full terms are not, I wouldn't think they'd be open yet. Okay, that's that. Shortly after midterm, which I'm guessing will be sometime next week, they will ask for midterm progress reports. And this class has been one of my better classes is getting first test done. That's 8 out of 10 have submitted the first test. So please, if you haven't done the first test, get it in. Or you can get your research paper in. That would also be a score. If I don't have some sort of score, by whenever they ask for midterm progress reports, I have to report that you have an F at midterm, which I don't want to do. Okay, so because no one seems to be close to that. They do want for any D's or F at midterm, and those who have submitted the first test, none of you have D's or F's. It's only the people who haven't that I would have to do that. And Christian decided to show today. I believe I announced that one. Oh, and Devontae is here. Good deal. Just been saying that if you are in a first mini-term course, the student course evaluations are now open. Please get those done. Today's the last day of first mini-term, and that means that second mini-term starts tomorrow, which means we are currently at midterm, and that means shortly thereafter they will be asking for midterm progress reports, which are anyone who has a D or an F at midterm. And if I don't have a score, guess what that is? Not a D. Okay? All right. So please get me something sometime this week or next week. Okay. Now, let's get on about what's available this week. I think I told you last time. I'll repeat it again because we may have more people here now than we did then. I will not be on campus tomorrow morning at 8 o'clock as I normally am. I will be on the way to Tuscaloosa. In fact, I should be very close to, if not in Tuscaloosa, tomorrow morning at 8 o'clock. Because I got a meeting. They say it's an all-day meeting, but of course with state, the headquarters people down there at the state, an all-day meeting means it'll end about 3:30. Okay, so I will be getting out of the meeting whenever it ends, around 3:30 or so. Then I'll be driving back, and since I'm coming right by campus on the way from Tuscaloosa, I'll come into campus and I'll be here until 6, because those are my normal working hours on, well, every day except Wednesdays when I'm here till 6:30, Fridays when I'm supposed to be leaving at noon. So tomorrow I will be on campus, but it'll be late in the day. I'm guessing around 4:30ish or so, and I'll be here till 6. So if you do want to get me something and I'm not here, you can slide it under my door. Does everyone know where my office is? Okay, good deal. If you don't, I'll point it out to you right after class or show you on the map right there where it is. So please get me stuff. You can turn it in tomorrow, and I will be here tomorrow evening to possibly grade it and get things caught up. Okay, that's first. Friday, I should be on campus my full, at least 4 hours, probably more than 4. 8 to 12. I do have a doctor's appointment at 2, so I'll be, if I have to stay late on campus, I can't stay past 1:15 because I need to get to the appointment by 2 o'clock. Hopefully I'll be away before 1:15, but you never can tell. But I can't stay any past 1:15 on Friday. Okay, the next week is back to being, I hope, a normal week as far as office hours and stuff goes. Now, I also had a doctor's appointment yesterday. That was my hematologist, and I found out, and this explains some things that I didn't know needed explaining, but as I got to thinking about them, I realized they did. I do get treatments 2 or 3 times a year for the leukemia, and it's a great drug. It has knocked the white cell counts right down in the normal range, and sometimes below the normal range, but of course they always climb back up. This is a disease, like the nurse said, they don't have a cure for it yet, but we can treat it. So it's sort of like diabetes. Very seldom they cure you of diabetes, but you can treat diabetes, okay? Well, this is a lot like that. The white cells come back up, and then they knock them down. Well, at the same time the drug is knocking down the white cells, it also usually knocked down the red cells some too. So I'd be somewhat anemic, okay? I've been that way ever since I've been on the drugs. Until yesterday, and the treatment I had back in January really knocked down. So the white cells, yeah, they're within normal range 3 months later, but the red cells are very anemic now. So that sort of explains why I have had so little energy. I thought it was because I was 69 years old, and I'd never been 69 before, so I thought this is just how it was, okay? But I found out that probably a contributing factor. So if sometimes it looks like I'm dragging, I am, okay? So I'm going to go on some B12 to help boost that. They said my iron looks good, but it's probably the processing of it. But I think what he's worried about, and he did 5 more blood tests. He did blood work beforehand, the standard stuff, and when he saw the anemia, he had me do 5 more blood tests. I don't know what the results of those are yet, and I don't know what they were yet. But I think he's fearing, my wife read up on it some, there is sort of a chemo-induced leukemia, meaning that it's not just that it knocks out the red blood cells, but it actually starts coating them and destroying them. So it's something I may have to get treatment for the treatment, so I don't know. We'll see how things go. I hope it won't interfere with school, but we'll see how it goes. So anyway, that's beside the point, but I just wanted to let you know in case I start, well, I hope I won't have to miss any classes, but in case it happens, you'll know ahead of time. All right, any questions before we get going today? Okay, yeah. Okay, like on YouTube? Okay. Now, if you're looking at the old lectures on YouTube, and here's the other thing, and just for, I'm glad you said that. I said earlier, before I started recording, that Screencast-O-Matic and YouTube were having difficulties. Now, I don't know what the difficulty is, but for most of the days last week, Tuesday, Wednesday, and Thursday last week, anything I recorded afternoon would not load. It would get halfway. Well, halfway is when it gets processed on my computer, and then the second half is when it sends it to YouTube. It would get stuck at 50%, stop there. I'd retry, I'd try to do everything I could, and nothing would happen. So I had to can it and just retry it and start over from scratch. Every day last week, including the weekend, when I'd started in the morning, it would load. The stuff that was backed up from the afternoons before would load. So, I don't know if this is what you're asking about, on Monday's class, which last week loaded fine. This week did not, and even Wednesday's class loaded fine because it was early afternoon. But Monday's class, it was trying to load in the afternoon, it wouldn't. So I've got this class, Cal 3 class, differential equations class, and my class yesterday morning. But because I was at the doctor's office, I missed 2 classes yesterday, so I don't know what they're doing. But those 4 classes, all 3 of Monday's classes and the 1 class I recorded yesterday, they have not. They're trying to load now. Hopefully they will because it's morning. I can't guarantee that because it used to be early afternoon still loaded. I don't know if it's doing that now or not. We'll see. So if you're looking for the last class, it's not out there yet. It's trying to load. It or one of the other classes is trying to load right now. Okay. I'll let you see. I don't know if you really care. Let me. Okay. I will pause. See, this is Monday's class, and this, I corrected this, but it doesn't show up here. This is Monday afternoon's class. This was Monday later afternoon's class. That was yesterday morning's class. And this one, no, this one is the one trying to load now. It's got up to 39%. We'll see if it goes over 50. But they have all tried and tried and tried. And I thought maybe it was something to do with here. I was at the farm in Georgia with a terribly slow DSL computer link up. It wouldn't load in the afternoon, but the next morning it did. And that was with a dreadfully slow DSL. So it seems to be a Screencast-O-Matic YouTube thing, and I don't know why they're not loading in the afternoon. Okay, enough of that. Was that what you're asking about, or the previous email, previous YouTube videos? Mondays, yeah, that's where Mondays is, still trying to load, okay? And I'm sorry. But we got up to page 172. We're in Chapter 3, Differentiation, 3.5, Implicit Differentiation, and we were doing Example 5. We got started on Example 5, and just to let you know what we did, it says determine the slope of the graph of this equation. This is not a function, you'll see later. It's an equation, okay? What is going to tell us the slope of the graph? The derivative, okay? And at the point here, and we already verified this point is on that graph, so we need the first derivative of this. Now, my question to you was, how many of you want to square this binomial, multiply that out, and then try to solve for y and see if we can take the derivative explicitly? Please say nobody. Nobody. Can't do it. It won't work. I don't think there's any way in the world you can make it work. You have y's here, y's here. There's no way. So we're going to have to do implicit differentiation. So let's real quickly tell me how we implicitly differentiate that. Let me get my pen set up. If the pen will set up. There we go. Someone tell me. Okay, 3 times 2, got it. To the first power, because you reduce that by 1. Excellent. Times 2x. Excellent. Okay. And then on the right-hand side, 100 Oh, wait. Sorry, we weren't through with the, wait, yeah. I got too carried away with how good your answers were so far. Okay. Duh. All right. The 2x was the first part of that innermost part, but we didn't do the second part. What was that? Plus 2y. dy dx. I'm just going to write it y prime because I'm lazy, okay? It's a lot less writing that way, but the prime is not sure. There it is. Okay. So now we've done the left-hand side. Now let's do the right-hand side. What would that be? 100 x x y prime, that's good, plus y closed entity. Is that what you said? Excellent, excellent. That was product rule if you didn't recognize it, right? Okay, the 3's and the 100 are just constants. They are out front. They don't have anything to do with much of anything. This 2 came from the exponent here times this. This is chain rule. 2 times this to the first power times the derivative of the internal part, the inner part. That's 2x. And then the implicit part, 2y times y prime. Okay? And then over here, the 100's out front. And this is the product rule here. First times derivative of the second, plus the second times derivative of the first, and derivative of that. Excellent. Way to go. Next. Ooh. We wound up with a product of two polynomials anyway. Now, what I wanted to do and did, just to let you know, I factored this 2, see a 2 is in both of these terms inside there. I factored it out and put it out with the other constants. So that's a 3 times 2 times another 2. That gave me a 12. Okay? Now, I'll write out what's left then. X squared plus y squared times, I factored out the 2, so it's x plus y prime. That's on the left-hand side. And on the right-hand side, let's go on and multiply it through. 100 xy prime plus 100 y. We're going to do that on the left too, but we first are going to multiply these binomials. And that's a good old foiling problem. So what does that give us? X cubed plus x squared y prime, good. XY squared, is that what you said? Excellent. Okay. And finally, y cubed, right? Squared times y, right? Y cubed, y prime. Okay, we've got that done, and this is equal to the right-hand side. We'll come back and write that again. Now let's multiply through the 12. 12x cubed plus 12x squared y prime plus 12, I forgot my 12, xy squared plus 12 y cubed y prime is equal to 100 x y prime plus 100 y. Agreed or not? Did I mess anything up? All I did was distribute 12 through there. By the way, there's no like terms. I kind of skipped over that. You always try to provide like terms. There aren't any, I'd say, on either side. Okay. So, what next? Everybody agree this is okay? Ugly, but okay. Okay, what do we do now? y primes on one side and all the non-y primes on the other side. So here's y prime here, right? A 12x squared y prime. Here's another one, plus 12y cubed y prime. Okay? That's all the ones from this side. Then we're going to subtract. Can I do this without writing it down? Subtract 100x y prime and move it over. Okay. Minus 100x y prime. I'm teaching pre-calculus algebra and some other courses that I usually do every step. Y'all are so sharp. Y'all don't need every one, do you? Let's say okay, never mind. We'll leave it alone. All right. That's all the y primes on the left. Let's get our right-hand side done. We started out with 100 y. That's the term without, because we already moved this one over there. And we got subtract a 12x cubed. That'll take care of that one. We already got this one down here. We need to also subtract a 12xy squared. So this one is going here. Oops. This one's going there. This one's going. That really makes it clearer, doesn't it? It's ugly. But you see what we got? 3 y prime terms on the left, 3 non-y prime terms on the right. Okay. Is this about where we left off last time? It seems about that way. So, what are we going to do next? Anybody? Why did we get the y primes together anyway? Family reunion? No, why? That's what we're looking for, the y prime. Isolate that. So factor it out. Y prime times. Now, what they do in the book is a little different from what I've been doing. They go back and recombine things or didn't take them apart in the first place or whatever. Here on these first two terms, they all have a 12 in them, right? And they all have a y in them, both of them, right? So I guess they pull out the 12y. And then the innermost part of that for the first one is a x squared. And what's left after a 12y comes out here is a plus y squared. Okay. So that's what they've done to this one, minus 100x. Not much you can do with that. Okay? I think they do the same thing over here. We'll leave the 100y alone and then subtract out factor out a 12x here, and that leaves you with an x squared plus y squared, because we factored out the minus out of both terms. I don't see that as a whole lot better. Okay, you see what we did? Not? Okay. Where? Is this line okay? Okay, that line's okay. So what we did here, we factored out the y prime, right, out of all three terms. So they're out. Okay. Now the first two terms here, without the y primes in them, they've got a 12 and a y in both of those. So let's factor that out of those two. And that leaves us an x squared here plus a y squared there. Close that out. So these two are those two coefficients. Is that okay? Okay, because we factored out a 12y. 12y here, leaving us an x squared. We already got the y prime out. And here we pulled out the 12y, leaving us a plus y squared. Okay, so that's this part, and then this one just came down 100x. Because we already had the y prime. Over here, we did almost the same thing. Bring down the 100y, minus 12x here. Now, we pulled out the minus from both of these and the 12 from both of those, and 1x from both of those. Okay, leaving us just an x squared here plus a y squared there. minus sign. Okay. Now, I don't know why that's any better, but that's how the book did, and maybe it'll turn out being better. Okay, I doubt it, but we'll try. What do we do now? What was the whole purpose of this whole exercise? Find the derivative. There's a derivative. But it's messed up with all this stuff jumped along with it. So how do we undo that? Put it over there. Right? This is all multiplied by this. So just divide and put it over there. Divide this side by this ugly thing of 12y times x squared plus y squared. Close that, minus 100x. Okay, that whole thing will divide over here. 12y times x squared plus y squared minus 100x. Okay, that is gone, that's gone. It's all over there now. Everything without a y prime is on the one side, with missing one parentheses, and only a y prime is left on this side. That's what we're looking for. Y prime evaluated where? At this point, 3, 1, right? So, guess what? What does the 3 stand for? X value, and the 1 stands for the y value. Plug them in. Just like the lathe. Now, I'm out of room. I'm going to start over at the top, erasing like crazy, okay? And I think we may answer our question. Okay? This will be y prime is equal to, this is from down here, 100 times what? And what is your y? 1. Okay, I can do that, I think. Minus 12 times 3 times 3 squared plus, say again? 1 squared. Okay, we'll write it all down. Over 12 times 1 times 3 squared plus 1 squared, close parentheses, minus 100 times 3. Okay, I'm going to erase some more. Okay, all right. All right. Okay. So let's figure out what this y prime is. 100 times 1 I think I can do. Okay, that's 100. Minus, let's go and do the 12 times 3. What's that? 12 times 3? Huh? Right here. 36 times 9 plus 1. 3 squared is 9 plus 1. That would be 10. Okay, I can do that one. Over, I can do 12 times 1 is 12 times 10 minus 300. Okay, let's see if we can carry that a little further. This will be 100 minus 360. Okay, got it. And 12 times 10 is 120 minus 300. And that will be, I think, something like negative 260 divided by negative 180. Okay, I'm sorry I talked so long this morning we didn't get more calculus done. Okay. All right, let's see if we can reduce some stuff. The minus over minus is going to be plus. The zeros can come out. And 26 divided by, what, any common factors between 26 and 18?
Say again? 13 over 9. That is a nice slope, isn't it? Determine the slope of that graph at that point, 13/9. Just what I was guessing. Weren't you? Okay. And that certainly is what they got. 13/9. Now, that's how we did it. You want to see how they did it. Does anyone need this left up here a little bit longer? Yay or nay? No? Okay. All right. Well, they did their solution by taking d by dx, and let's see how they did it. They did the 3 times 2 just like we did, times x squared plus y squared to the first power just like we did, times the root of the inside, 2x plus 2y dy dx, just like we did, only have to put y prime. Okay, pulled out the 100 and x dy, y prime, plus y times 1. That's the dx dx. That's what we want. We just left off the 1. We just left it as y. Multiplying these together, they didn't show any of that. They just said, hey, this is what you get at the end. Oh, and they even moved them from side to side. So they didn't skip many steps, did they? Okay. So don't you follow this? That's a lot clearer than my way of doing it, isn't it? Yeah, it just magically appears. Okay. But anyway, that's same thing we had. And after I factored the way they did, just so it would look the same. And then they factored out the dy, dx's, and then they divided by the coefficient, this is up front, and they rearranged the order, and I don't really know why, but they did. Perfectly fine to do it. I don't see why they wanted to do it, but they did. Okay, I guess just to get the 12s and the x squared plus y squared over on top of each other and the hundreds. I don't know. There's no real reason to. And then they factored, which is fine. They divided out, a 4 from every term, which is a good thing to do. Nothing wrong with that. And then they proceeded to plug in the values and do the math and get that and reduce it to that. So they showed you those easy steps in full detail. It's the hard stuff they just skipped and put about 15 steps at once, okay? But that's a good way to write a book, isn't it? Okay. Now, here is the graph of this, where we can't see, oh, here it is, that thing again. This is called a lemniscate. Why, I don't know. I guess that means something to somebody. Here's the 0.31 that we verified was on there. Sure enough, this slope there appears to be something greater than 1, probably less than 2. Yeah, you got it right. All right, any questions on that? Is that a function? No. The vertical line test fails miserably in many locations, but it is a graph of an equation. All right, good deal. That's example 5. Any questions? All right, they're skipping example 6. Shame on them. All right, so let's do example 6 here. Determining a differentiable function. Okay. Find dy dx, so that's what we're looking for. Dy dx, that's what we're looking for. For the equation sine y is equal to x. Okay? Then find the largest interval of the form minus a less than or equal to y less than or equal to plus a, over which y is differentiable function of x. And they draw the figure. Shame on them for not putting it on the slide set, so making me draw it. Okay? First, how do we find dy dx given this function or expression, equation? How would you do it?
Help me somebody, huh? Sines do, yeah. But this is sine y, and we're looking for y as a function of x. So you could, if you really wanted to, do the inverse sine of both sides, and then take the derivative of an inverse sine. I don't want to do that, okay? But you could do it if you wanted to. But let's do it implicitly, which is usually a lot easier. So how would you do that? First step. What is the first thing you see? Sine y. What's the root of sine y? Help me, somebody. Derivative of sine. Cosine. So that'd be cosine y. But now we chain rule it. What would that give you? You did the outer function, now you do the inner function. You're doing dy dx. That's what we're looking for. Isn't that what you get with the chain rule? Dy dx. The derivative of the outer function times the derivative of the inner function, which is y, and the derivative of that is dy dx, right? Let's take the derivative with respect to x of the right-hand side, and what's that? One. That's it, okay? So, if all you're looking for is dy dx, here it is. Dy dx, you could divide both sides by cosine y. So this is equal to either 1 over cosine y, or if you wanted to express that differently, that would be, what's 1 over cosine y? Oh, I got to contact your trig instructors. Oh man, oops, I was 1. Yes, secant y. Okay, that's it. Dy dx is secant y. Okay? Now, they didn't write it as secant y. They left it as 1 over cosine y, which is fine, perfectly fine too. Okay? Now, why, but they did. It said find dy dx implicitly from the equation that. We've done it. Either this or that. Either answer is correct. Okay? Now, it says then find the largest interval of the form minus a is less than or equal to, no, less than y is less than a, on which y is a differentiable function of x. Okay? Now, as Houston was saying, if we had y is equal to sine x, it would look like this. Right? And that's not what we got. This is y is equal to sine x. What we have is x equals sine y, or sine y is equal to x. So what we would do then is do our function like this, and then do, let me see if I can get it right. Is that going right? Yeah. Something like that, okay? With a problem here that to be a function, you has to be one to one, 1 to 1, okay? To have an inverse, and that's what we're sort of dealing with. So it would go from here to here. Here is the values over which you can draw that. It says find the largest interval of the form minus a less than y is less than a, on which y is a differentiable function of x. It's differentiable only on this thing. Why? Because here you have a vertical tangent, not differentiable there. Here you have a vertical tangent, not differentiable there. So it would be from, and what is the value here for, and it says for y. I don't know why they chose y, but they did. That would be minus pi halves less than y less than pi halves. Normally we say it has an inverse including those endpoints, but it's not differentiable at the endpoint because those are vertical tangent lines there. So that's what they're looking for there. Not much of a an explanation of why. Now, if you're wanting to know how they got to that algebraically, this is where they say if you wanted to do it explicitly as a function of x. And they're only talking about the derivative formula there. And they rewrite this as 1 over, and cosine is square root of 1 minus sine squared. I don't know if you remember that or not, okay? But that is what cosine is. Because sine squared plus cosine squared is 1. So cosine squared would be 1 minus sine squared. And then take the square root of both sides, and that would be the positive principal square root of that, if you're staying with the positive. Okay. And so, I don't know why they proceed this way, but they did. But then the sine y, from what we have here, that's equal to x. So this is 1 minus the square root of 1 minus x squared. That's how you get an answer that is explicit. Now, there you're talking about the x values, and you know x has to be between minus 1 and 1. Because anything outside of 1 just gives you a denominator you can't deal with. And in fact, it can't even be 1 to minus 1, because then you have 0 in the denominator. So that's why it's from this point, not counting that point. So if I can erase some of my ugliness here, not all of it, but some of it, okay, and put an open circle here and an open circle there. That's expressing in terms of x, that's going from minus 1 to 1, y is going from minus pi halves to pi halves. This is going from minus 1 to 1 on the x. Okay.
So then is where it's limited?
What's that?
So that's where it's limited?
Yeah. That to be the largest interval over which the function is differentiable. It's differentiable everywhere from here to here, but not here or there. So that's why you have open circles there. Okay. So it's differentiable everywhere else. It's not a function beyond that, okay, to be a function, it has to be between these two, but to be differentiable, it has to be inside that and inside that. And these are the values of x, and these are the values of y. Okay, they're also skipping example 7, which I think we need to do. And they do talk about a guy in the margin here named Isaac Barrow. He was an English mathematician, a very good English mathematician, an exceptional English mathematician. He was head of the He was Lucasian Chair of Mathematics at Oxford University, which is about as high as you could get in England of being a mathematician. And he happened to have a student, had many students, but one of these students had a name of Isaac Newton. Can you imagine having a student of Isaac Newton? Probably within a few short years, Newton had eaten up every bit of knowledge he could get from Isaac Barrow and moved on from there and started developing things way beyond what Barrow had ever conceived. And Barrow had to have been a really quality individual, because you know what he did? He stepped down from his chairmanship to give it to his student, because he recognized his student's brilliance and said, look, he can take you way further than I can. He's already passed me. So he did. They corresponded frequently regarding their work. So Barrow probably had a hand in the development of calculus. Newton's given the credit for it, but Newton went to his mentor, his professor, his leader, and moved from there. So anyway, Barrow had developed, before Newton, a thing called the kappa curve, and I think that's what the next equation is dealing with. I don't know, but they have it in here for some reason. So anyway, let's go to example 7. Here's an equation. X squared plus y squared, this can't be it. X squared plus y squared is equal to 25. Does anyone know what that is? It's a circle, okay? All right. I should draw the circle first and then draw my thing around it. With what? What are these points here? 5. Radius 5. Circle of radius 5. Okay? Squared. X squared plus y squared equal r squared. Okay? So, in terms of functions, they are two separate functions. Give me a color. Red. There's the upper function here, and give me another color. Blue, Carolina blue. Okay, got the Carolina fans in here again. And there's your second one. Okay? Now both of those are functions of y as a function of x, but the total is not a function. Okay, but those are y as a function of x. Okay? And it could be written as y is equal to plus or minus the square root of 25 minus x squared. That's how you get it. The plus is the red one, the blue, Carolina blue is the lower one. That's the minus sign. Okay. That's not what they were interested in. They said, given that, let's find a second derivative based on that function. So what must we do first? Anybody? Yes, let's take a first derivative. And what does that give us? Let me go back to black. 2x plus 2y dy dx, or y prime, is equal to 0. Okay. Now, in my mind, the easy thing to do is solve for y prime. That's not what we're looking for. We're looking for d2y dx squared. But let's not jump the gun. Let's solve for y prime first, dy dx. Probably I should be writing it that way. What would that be? What would you do to solve for that? Subtract 2x from both sides? Is that what I heard? Yes, okay. I don't hear well either, okay. And that gives us 2y, y prime, I should be writing that as dy dx is equal to minus 2x, and then divide by 2y. Perfect. Okay? Everything goes out here except the, I'm going to write that as dy dx now, is equal to, and the 2's go out, minus x over y. So, how do we get the second derivative of y with respect to x squared? We do d by dx of this and d by dx of this. Oh, put an integral there. Ooh, where was I thinking? Okay. For some reason, the pen's not wanting to come back because I've made such a silly error. Okay, I think it came back. D by dx of this. I was trying to get the minus sign outside, but I don't have room for it, so I'll just do it that way. Okay? So, what would that give us? This on this side is our d 2y dx squared. You see where it comes from? 2 d's, d2y, and 2 dx's, dx squared. Okay? And what would this be then? Guess what rule? I'm going to put the minus sign out front. Now I can. Where would you go from there? What kind of rule? Quotient rule. One of my favorites of all time. What would that be? Say again? Dx squared, is that what you said? How does the quotient rule go? Low d high. Well, what is your low? Y times dx. And what is dx? Derivative of x? 1. Okay, so it's y minus well, not quite. High d low, right? High d low. Okay, never mind. Okay, that would be x. And what's d low? No, it isn't. Not quite. Chain rule. Not really a chain rule, it's just y prime. Right? Implicit differentiation. All over low, which is y squared. All right. Now what I'm going to do is use that minus sign to reverse the order inside. And this is going to be xy prime minus y over y squared. Agreed? Except that they wanted d2y dx squared. Now, usually when they're looking for a derivative, like the second derivative here, it's not a great idea to have the first derivative stuck inside of it. But we already know what the first derivative is, don't we? That is minus x over y. All right. From here. So let's plug that in here. So I'm going to erase this and write it here. d2y dx squared is equal to x times, and dy dx is a negative x over y minus y over y squared. Now, we don't mind having y squareds in there. I don't particularly like them, but they're easy to write in a bunch of square roots in there. So we'll do that. And generally, what do we have to do when we've got something that's like that? I call it complicated fraction. Most of the early algebra books call it a complex fraction, which is okay, but it's complex to be the square roots of I mean, imaginary number I. So let's not whatever you want to call it. How would you go about solving
or simplifying something that looks like that? That's going to be hard. We want to leave a denominator here. We want that out of the denominator of the numerator. We don't want a fraction within a fraction. This part of the fraction's got to hang on to. So how do we get rid of this one? That one. Multiply everything in the numerator and the denominator by y. Well, what's y over y? 1. What can you multiply by 1? Anytime you want to, because it doesn't change the value any. So we're going to multiply every term in the numerator by y, and every term in the denominator, which is only 1, by y. So that first term gives you and you got two minuses here, because I'm going to pull the minus on the outside. And this y here is going to wipe out that one. So you get a minus x squared. And then you're going to have a plus y squared, because I pulled the minus on the outside. Okay? And that is over y cubed. Okay? Now, anyone recall what x squared plus y squared is? Huh? Yeah, but what is it? It's 25. So this is minus 25 over y cubed. Ooh, that's pretty simple, isn't it? Who would have thunk it? Okay? And that's indeed what they got. Minus 25 over y cubed. So I don't know why that was listed by Isaac Barrows talking about the kappa function, because that's kappa curve. That's not a kappa curve at all. But that's okay. But they also left off example 8. So can we move from example 7 to 8? Okay, so let's do that. The point here, I think that he was trying to make is, whenever you get something like this, simplify it, and then see like in your original problem if you can simplify anymore. Like for instance, when having a y prime in your second derivative, that's not good because you know what y prime is, so plug that in there, simplify that, and then you wind up with having this here, which you can simplify again. You still got a y in there, and not much you can do with it, but that's a fairly simple answer. All right, so example 8. Okay? Find the tangent line to the graph of x squared times x squared plus y squared equal y squared at the point root 2 over 2, root 2 over 2. Okay? As shown in the figure here. Now this looks like it's, this is the kappa curve. Doesn't look that much like a kappa to me, but it's okay. We'll call it a kappa. Okay. Now, cynic that I am, I want to make sure that this point is indeed on this curve before I waste any time. Spend any time trying to verify something. So let's plug in our x value here. What do we get when we square root 2 over 2? What is the square of root 2 over 2? It's what? Not 1. Square root 2 and you get 2 over square 2 and you get 4. 2 over 4 is 1/2. So here's a 1/2 here. Times, and this is a 1/2 times, plus 1/2. 1/2 plus 1/2 is 1. 1/2 times 1 is 1/2, and 1/2. Yeah, 1/2 equals 1/2, okay? Yes, that point is on this curve, okay? So now I'll spend time doing what they're asking for. Find the tangent line. What do we need to be able to give you a tangent line? You need two pieces of information to do an equation of a line. Okay, a derivative will give you what? A slope. And what else would you need? A
slope and a point. And we got the point already. So all we need is a slope. So that's why we take a derivative. Now, let's multiply them all out and solve for y. And you want to do that? I'd rather not. So how might we do it? Say again? Okay, implicit differentiation, which we'll use the chain rule among others. Okay, so how will we begin? Okay, what rule are you using first? Say again? Okay, what rule are you using first? What does x squared outside of parentheses of x squared plus y squared mean? What operation? Multiplication. So we're using the product rule first. Okay? So you were starting with first, which is x squared. Is that where you're starting? Okay, so x squared times what? No, derivative of the second, right? First times derivative of the second. What's the derivative of the second? 2x plus 2y, say again, dy dx, or y prime. Okay, I'm just lazy. Okay, that's the first times derivative of the second. What follows that? Plus 2x times x squared plus y squared. Okay, this second time derivative of the first. Okay, and take the derivative of the right hand side, and what do you get? 2y, y prime. Excellent. Okay, now we got some more business to take care of here. Let's multiply through, and this gives us 2x cubed plus 2x squared y prime, right? Yay or nay? Okay, plus 2x cubed, right? Plus 2xy squared, right? Is equal to 2y prime. Agreed or not? Okay. Before we proceed any further, do you notice anything you might be able to get rid of? I'm just lazy. I don't want to haul around anything I don't need to. It's my anemia. I get tired if I haul around too much, you know. It's what? Well, not that. Simpler. Or did you say 2? Oh, okay, yeah, that's right. Divide out of 2 from every term on every side. Okay. Now what do we want to do? What's the whole purpose of this? Get the y prime by itself. So here's a term with y prime in it. X squared y prime. We're going to have to drag the other one from the other side. Minus y prime. Okay, ooh, maybe I don't want to do it this way. I don't think I do. I'm just real lazy this way. I don't like minus signs that much. They trip me up most of the time. So, what I'm going to do is move them to the other side. So this will be a y prime minus an x squared y prime. Is that okay? Okay. And then this side will stay the same. I don't have to change signs. And this will be an x cubed. Oh, x cubed plus x cubed. What's that? 2x cubed. And then you got a plus xy squared. Right? You agree? You see what I did? Okay? It was a little tricky. I moved this y prime to this side. Now flip sides. Okay? So this was this one minus this one.
this side now, and what's here is on the other side now, and that's x cubed plus x cubed. These are the terms of that y cubed then. 2x cubed plus xy squared. Yay? Okay. Now what? What's next, folks? Help me. Getting really tired. Say again? Well, we sort of did, but you extract the derivative, if that's what you meant. That's what you meant, right? I thought so, okay? And what do you mean by that? Yeah, factor it out of both sides. That's a y prime times what's left. I mean, out of both terms. Times what? Y, why not? Minus x squared y is equal to this mess. 2x cubed plus xy squared. Okay? And now what? What's the whole goal of this? Divide by the y. Yeah, I can't write. Okay. Goodness, I'm hungry. Minus x squared y divided by y minus x squared y. Okay. So there's our y prime. Now what would we do? Plug in the x and the y. That's a great idea to do. Now, I don't know, is it better to factor out the x's first? Do you think it is? And the y's? Is that going to make it any easier or not? What you think? Or just plug in the way we got it? Which way you want to go? Say again? Okay. Here's an advantage to factoring at this point. On the next step, anyway. Let's factor out an x from the first term. That's all we can get out of there, right? X times 2x squared plus y squared, right? Now, this isn't simplifying things right now. In the denominator, you can factor out a y, and that leaves you a 1 minus x squared, right? Here is the only advantage to doing that, because your x and the y are the same values here, aren't they? So when you plug them in, this is going to be root 2 over 2 over root 2 over 2. So in effect, not in every xy, but in this xy, they go out. So I found that just a little bit easier to do. Okay, so let's plug in our other values here, and this will be 2 times, what was x squared? We did that, didn't we? Please say yes. We have long memories, right? Like 5 minutes ago. What was square root of 2 over 2? Squared? Huh? 1/2, wasn't it? Okay. 2 times 1/2 minus 1/2, because that's the y squared there. I don't know where the lower half went. There's our numerator there, and our denominator down here is a 1 minus 1/2, isn't it? Okay, well 2 times 1/2 is, anybody? 1 minus 1/2 over 1 minus 1/2. Guess what that is, folks? One half over 1/2? 1. There is the slope. All that for 1. Okay? No, it isn't. They say it's 3. Where in the world did that come from? Oh, my goodness. No?
Where did I get a minus sign? That's a plus sign. Sorry about that, folks. That's a plus sign. There's a plus there, and that's where that came from. So scratch this if it itches, okay? So that would be 1 plus 1/2 over 1/2. So that's 3/2 over 1/2. And that is indeed 3. Okay, there's our slope. That just gave us a slope. They're looking for the tangent line. So how do you get the tangent line out of that? Help me somebody. What do we use? Say again? The tangent line. Find the tangent line. It's been missing for a while. Okay, we got the slope is 3, and we got a point right here. So how do we use those to get a tangent line? Oh, how does that go? Which is y minus root 2 over 2 is equal to 3 times x minus root 2 over 2. Okay? Now, I don't know about you. If you don't like the fractions in there, you could multiply everything on both sides by 2, and that would give you 2y minus root 2 is equal to 6x minus 3 root 2. I don't know if that's any better or not. That depends on your preference. I don't know. How did they leave it? Well, let's carry on. 2y, add root 2 to both sides, is equal to 6x plus 4 root 2, right? No. Add, yeah, plus 2 root 2. Right? If you add a root 2 to both sides, you have 3 root 2's, you add 1 to minus 3 root 2, add a root 2, you get minus 2 root 2. There, that, see, the minus signs just slip up and snag you every time. That's a minus there, not a plus. Okay. I hope. Okay, yeah, it is. Okay. Now, here again, we can divide everything by 2. And you get y is equal to 3x minus root 2. And that's what they got. Now, that's not the only way to get there. I probably got there going around my elbow to get to my ear, but there is the answer. Yes?
Right here, y minus x squared.
It's not because those can divide out. It's because when we plug in root 2 over 2 and root 2 over 2, they're the same numbers. And that's only because of that. It's not for x and y. I just didn't want to write all that down, but that's root 2 over 2. I was going to write it down here, but I didn't have room, so I just took them out here. Because that's the same number. And then we just had this, and that's where the plus sign came from. And this one is 3/2 over 1/2. You could have done it by just subtracting root 2 over 2 from 3 root 2 over 2 to get 2 root 2 over 2. I did it a little bit longer way. But there's your answer. All right, good questions. Any others? All right, that was example 8. Now finally we're ready for logarithmic differentiation. So you have to pick this up on YouTube. Okay. All right, we already did that, and that, and that, and that. So now let's look at logarithmic differentiation. On occasion, it is convenient to use logarithms as aids in differentiating non-logarithmic functions. That sounds like it would be more complicated. But guess what? That process is called logarithmic differentiation. When in the world would that make sense? Okay? Well, here's one. Find the derivative of this thing. Okay. When does it make sense? When you have exponents in there. And you have x's in your base and x's in your exponent. Ew, what a mess. But if you were to do this, take the log of both of those. Now remember, you're only looking for y prime. But if you take the log of both of these, what's the log of, this is just log y, right? Now we're doing natural logs, right? What's that? Oh, you're right, aren't you? Whoa. Okay, let's back off. Okay. And let's do example 9. Find the derivative of y is equal to x minus 2 squared over the square root of x squared plus 1. Now they have a little side note here saying that x cannot equal 2. Okay? And the reason for this, if x is equal to 2, derivative of this is obviously 0. Okay? Because when you put a 2 in here, y is equal to 0. Well, no, it's not. Derivative is not necessarily equal to 0. Y is equal to 0. And we'll see later we have to exclude that. 2 would not be an issue at all down here. It's up here, and we'll see why that's true in a minute. So, does anyone want to use the quotient rule on this one? It looks like a lot of fun, but let's not, if we can get away with it. Because remember, logs make powers and roots much easier to deal with. So what we're going to do, and it seems bizarre, is to do the log of y. Now, what would be, and you might also want to do this. I think it's a good idea to write this as x minus 2 squared times, now, see, two things I don't like, things in the denominators and things under radicals. So how could I write that using exponential notation that gets rid of that denominator and the radical? X squared plus 1 to the negative 1/2 power, because it was in the denominator. Yeah, if you put it over, you do it over 1, x to that to the 1/2. I'm getting rid of the denominator too, so I'll make it negative 1/2. Okay? So I would do that first. Okay? Now take the log of that, and what do you get? Okay, I'll write it out in several steps. That would be the log of x minus 2 squared plus, because the log of a product is the sum of the logs, okay, plus the natural log of x squared minus or plus 1. I keep doing that today, to the minus 1/2. Okay, that takes care of the time sign there. You could have done it the other way too, with a minus by dividing, and that would have worked the same way. But here, let's take this one more step. Bring the 2 out front, because log of a power is the product of the power times the log. So that would be 2 times the log of x minus 2. Correct or not? Okay. Plus, or actually minus, because that's going to be a minus 1/2 the log of x squared plus 1. Now, can you do anything to simplify this one any further? No, you cannot simplify a log of a sum or a difference. Now, time out for just a moment. Here's why you see x can't be equal to 2. Okay? Because you're taking the log of 0, if that's the case. So that's why x can't be 2. That's right here. No problem with the original, but in order to do the logarithmic differentiation, you have to exclude x equal 2. Okay. So now we're at the point we can take our derivatives. What's the derivative of log y? Anybody? Say again? Oh, on what we've done so far? Okay. Now, I chose to rewrite this way. Are you okay with that? Okay. Now, when I take a log of this side, that's just log y. Okay? When I take a log of this thing, the log of a product is the sum of the logs. So that made it the log of this one plus the log of that one. Okay? The log of a product is the sum of the logs. One is the rule for logarithm. Another rule for logarithm, the log of a power is the product of the power times the rest of it. So this became 2 times the log of the base. Okay? Now remember I said if you have a hierarchy of operations, addition, subtraction on the base, multiplication, division next, and exponents and powers up here. What a log does is take the exponent of power and make it a multiplication or a division. It takes a multiplication or division and makes it an addition or subtraction. So it took this multiplication, made it an addition. It took this power and made it a multiplication. Took this power and made it a multiplication. It can't do anything to a subtraction or an addition because that's always at the lowest level. You can't go any lower. Is that okay? That's my way of remembering that. Okay, so now we've got what log y is. What we're interested in is the derivative of that, of y. Yeah, find the derivative of y. This thing. Say again? Okay, but we're going to use this one. What's the derivative of log y? Anyone remember that one? Please say yes. Derivative of log. Oh boy. Anybody? 1 over. Okay. Even simpler than that. Here we are. Page 160. Theorem 3.13. d by dx of log x is 1 over x. But more to what we're doing here, d by dx, I love saying that, of log u is 1 over u d by dx of u. Or u prime over u. Remember that? Page 160, top of the page, in the box, huh?
So it'd be y prime over y?
Y prime over y. You got it. Okay? Or 1 over y times y prime, right? Okay. So this would be y prime over y. Okay? Is equal to, and this will be 2. What's the derivative of log of x minus 2? Derivative of log is what we just said, 1 over x minus 2. Okay? Minus 1/2. And what's the derivative of log of x squared plus 1? 1 over x squared plus 1. But you got a chain rule to deal with here. Times (2x), right? Because derivative of x squared, right? That's what you were saying, wasn't it? I thought so. Okay. You see that? All right. Now, let's simplify what we can. This 2 and that 2 will go away. Okay? They eloped or something. Okay. So what we have here is 2 over x minus 2 minus x over x squared plus 1. Now, in my mind, I'm okay leaving it just like that, except that we're looking for y prime, not y prime over y. So we want to take this thing and multiply it by y. And I would love to keep that as just y, but I have a feeling they're going to want to rewrite that y as x minus 2 squared over the square root of x squared plus 1. Now, I don't know that they wanted to do that, but I had a sneaking suspicion they did. Now, if we do that, though, we can simplify things a little bit, because if we multiply this first term by that, you get a 2 times x minus 2, because this x minus 2 will divide one of those out. Okay? So that really simplified a little bit. And then the second term would be a minus x wait. This is over the square root of x squared plus 1, because you had to multiply that by it too. Okay? And the second term would be x times x minus 2 squared, because you can't do anything with those, divided by, and here we have this to the 2/2 power, which is 1, and that's to the 1/2 power, so this will be the square root of x squared plus 1 cubed. We are out of time. Okay. Let's see what they do. Then they take this and multiply 2 times x minus 2 times x squared plus 1 minus x times x minus 2 squared. My pen is so slow. All of this over x squared plus 1 to the 3/2 power. That's how they wrote it. Ooh, that's ugly. And they actually multiplied. They factored out 1x minus 2 and then combined the rest of them together. It's a mess, but it's not hard to get from the last step to the bottom step in the book. That's what your y prime is equal to. That is a little messy at the end, but the front part was perfectly fine. So we'll begin next time. Sorry, I thought we'd finish this. We'll begin with example 10. Okay, homework exercises here include any of the odds 5 through 25. They're all at Calc Chat. 5's at Calc View. 27 or 29, both at Calc Chat. 29's at Calc View. 31 through 37, they're all at Calc Chat. 31's at Calc View. 39 or 41, they're both at Calc Chat. 39 is at Calc View. By the way, there's the Witch of Ignacy mentioned here. That's actually a couple of different paper topics. Since this class has turned in so many papers by now, which is 0, okay, a potential paper topic, hint, hint. 42, which you don't have to do, is the Folium of Descartes, which could be another paper topic or 2. Then you have 43 or 45. They're both at Calc Chat. 45 is at Calc View. I'm sorry. That was 43 through 47. All at Calc Chat. 45 is at Calc View. 49 or 51, both at Calc Chat. 53 you can explore doing. That's at Calc Chat. It should be. 55 should be at Calc Chat. 57 is both at Calc Chat and Calc View, sort of similar to the sign Y that we did. 59 or 61, both at Calc Chat. 61 is at Calc View. 63 should be at Calc Chat. 65 should be at Calc Chat. 67 should be at Calc Chat. And then any of the odds, you can start doing some of these, 69 to 79. They should all be at Calc Chat. 71 is at Calc View. If you want to hang on to those until we do the last one, you can. And we'll pick up the rest of those later. Good deal. All right, have a good weekend. Remember, I am not on campus tomorrow until late in the day, probably sometime after or around 4:30ish until 6. I'll be on Birmingham campus 8 to 12 on Friday. Okay. We'll finish, finally, section 3.5 next time and move on to 3.6. Not one of my favorite sections. Okay. That's beside the point. Okay. That's not what I wanted.